work through a notebook which illustrates how we go about coding up the solution to a boundary value problem for ordinary differential equations. I'll also post the notebook with a little bit more text in it, where the text will take the place of what I'm saying as we go through. So what we're wanting to do is we're wanting to think about the boundary value problem as opposed to the initial value problem for ordinary differential equations. As I've written here, an initial value problem, you specify the value of y and dy by dt at some starting point, t equals t0. Of course, y and t are both labels that we've just put in there. A boundary value problem, instead of specifying y and dy by dt at one time, specifies y itself at 2 times, t0 and t1, and I'm going to label those as y0 and y1. Actually, we're going to think about a projectile, so we're going to think about z rather than y, and I'm just going to copy and paste a little bit of text here that gives us the basic equations that we need. So we've got a projectile which is going to be projected with an initial velocity v. It's only moving in the z direction, and it's moving under the influence of gravity. So we have the usual kind of approach where we take the second order differential equation, which of course would be m d2z by dt squared is equal to minus mg, and we split that into dz by dt is equal to v, and dv by dt is equal to minus g. Notice we've cancelled the m on both sides of that second equation. And we're assuming the standard value, g equals 9.81 meters per second squared. So we need a function to return the right-hand side of those as a single array. There's going to be ball vertical RHS, and we're going to give it t comma y. We're giving t and y in that order because we're going to use the SciPy integrate module. And I'm just going to copy and paste the docstring that I've written for this function already, just to save time. So it's the right hand side for a projectile, t and y are there. So we'll define in the function g is equal to 9.81. I'll put a comment to say that's meters per second squared. We'll set z is equal to y of 0. V is going to be y of 1. And then dz is equal to v, and dv is equal to minus g. And so we return a NumPy array of dz and dv. So what that means is that we can evolve both of these first order ODEs simultaneously because we're returning the differentials of both of them. So let's now set up some initial conditions. We'll set, let's put a t in there where we need it. We're going to set t0 is equal to 0 in seconds. I'm just going to note SI units here in case I forget. T1 is going to equal 10. And the mass is going to equal 1. That's quite a hefty projectile if it's a sport. And we're going to put on some boundary conditions. We're going to say that Z0 is equal to 0.0, of course, in meters, and Z1 is equal to 0.0 in meters. So you could imagine this to be an attempt to hit somebody with a snowball or some kind of sporting-based metaphor. Personally, I support the 49ers, so at the moment I'm thinking about Brock Purdy dropping the ball into the hands of George Kittle at the right moment. You may think of cricket or football or any other sport you wish. So there's our initial conditions, and what we're wanting to do is we're wanting to integrate to solve the problem. Because it's a boundary value problem, we don't know what initial velocity we need. That's what we're going to try and find. So we have to guess. So let's do this manually to start with. I'll just illustrate the process manually. And we're going to start with an initial velocity of v0 is equal to 0.0. So it's not going to have any acceleration, any velocity in z, and we're assuming that there's no boundaries, that there's nothing stopping the ball from going in any direction whatsoever. Therefore, there's no ground. If we set y0 to be an initial array of z0 and v0, like so, then I'm going to calculate some kind of distance is integrate, that's the SciPy module dot solve IVP, and I'm going to give it the function ball vertical right hand side. I'm going to give it the tuple of the times t0 comma t1, and I'm going to give it the initial condition. That's all I have to do. And then I'm going to, once we've done that, I'm going to print, and I'm going to use formatted printing, and I'll say with initial velocity v0 meters per second at t is equal to t1 seconds, the height is now this is slightly tricky. We've got distance, so that's the sort of the compound object that's returned by solve IVP. So we have to break it down and extract y, which is just the record of positions and velocities. Now that has two indices. The first index chooses between position and velocity, or actually it chooses between the two components that we pass. And here we've set it up so that the first component is position, the second component is velocity. So we want position, so that's 0, and we want it for the final time step, which is -1. And I'll put meters there. So let's run that. There we go. With an initial velocity of 0 meters per second at t equals 10 seconds, the height is -490 meters. Okay, so imagine letting go of a projectile over the side of a cliff, having checked beforehand there was no one underneath you. And you can see that that's reasonable. So we've got one solution that gives us a negative height. What we need now is a second solution, a second guess for the initial velocity that gives us a positive height. So I'm just going to copy these and I'm going to change my initial velocity, let's say to 10 meters per second. Actually, let's put a unit here. What happens? Okay, -390. I have to make that considerably bigger. Let's make it 40. Still -90. Let's make it 60. Okay, now we have a positive height. So with an initial velocity of 60 meters per second at 10 seconds, the height is 100 meters. So we now have the brackets that we need. And if we wanted to, we could experiment. The first thing I would probably do is change the lower velocity, so the initial bracket where we set it to 0 to something like 40, and then we would home in. But that's not really the point of this. The point of this is to show you how to code this up. So let's do that. Let's put in a little section heading here, automating the search. Let's make it a second level section, like so. So in order to automate the search, we need to create a Python function that encodes the thing that we're searching for. So in any kind of root finding search, which is what we're doing, we're looking for the zeros of a function. In this case, we want the difference between the required height and the actual height to equal 0. So we'll create a function to do that. So we're going to have height difference. Let's just call it that, something simple and easy. Def height difference, and we're going to say v0, that's our initial condition, and z1, that's our desired result. In fact, let's put z1 required. So return the difference between actual height at t1 and required height. So inputs, what do we have as inputs? We have v0, which is the initial velocity. This is the independent variable. This is the thing that we change. Z1 is the desired required height at T1, and the output is going to be the difference between the actual and required heights. Good. Okay, so how do we do this? Well, we say Z0 is equal to 0.0. We say that Y0, oopsie, is a NumPy array containing Z0 and V0. And then we just use this call to the integrator up above. You'll notice that I'm assuming that we've got the T0 and the T1 defined outside. If I were writing this carefully, I would probably include them as arguments or something. So that's our distance, and now we can say that the error is equal to distance.y of 0, -1 minus z1. And yeah, we can put in some comments here. So initial conditions, solve for trajectory, whoopsie. and then find and return the difference. Let's call this diff rather than return diff. Okay, so that's a function which will return 0 if we've got the height right, and it'll either return a positive or a negative number if we've got it wrong. So now we just need to implement root finding. So let's do this as a simple bisection. So we'll define the target height here. Z1 is equal to 0.0 meters. Let's put in the initial brackets. V0 we know is equal to 0.0. We know this from above. V02 is equal to 50. No, I think I said 60, didn't I? F1, so that's the value, is going to equal height difference of V01 comma Z1, and F2 is going to equal the height difference of V02 comma Z1. So you see, this is all much tidier, and it becomes quite clear what we're doing. So let's just actually print that out, because it's a good idea to make sure we're doing sensibly. So brackets are V01 comma V02. Oops, let's put those in curlies, otherwise we won't get the value of the variable. There's a meters per second with height differences. F1 comma F2 meters. Let's just run that just to check. Okay, so we've got brackets of 0 and 60, and the height differences are minus 490 and 109. That means that we've done something correct. It's always a good idea to check that you're doing what you actually thought you were doing, rather than having got something wrong. Let's set up some parameters. Let's have a maximum number of iterations. I'll set that to 100. We'll set iteration IT is equal to 0. Now under tolerance, set it to 1 10 to the minus 3. And let's set the midpoint as just 10 times the tolerance, so that we can go into the loop. So here's our loop. You want the absolute value of F mid being greater than tolerance. In other words, we're going to keep bisecting while the current midpoint value is larger than the tolerance, and IT is less than maximum number of iterations. So there's our while loop. We'll just keep doing that, and we want to do a simple bisection. So our simple bisection is to set up the midpoint initial velocity, which is a half of V01 plus V02. We'll say that F mid is equal to the height difference of V0 mid comma Z1. And now we just need to check. So if F mid times F1 is greater than 0, then that means they've got the same sign, and so we replace V01 with V0 mid, because V0 mid is closer to the right answer, but it's still on the same side. And F1 is going to equal F mid, else V02 is equal to V0 mid, and F2 is equal to F mid. The computational load in this problem is trivial, but writing it like this means we don't have to keep recalculating. We don't have more than one function call per loop. Okay, so there's our bisection loop, and let's just put some output here. We'll say finished after IT iterations, because it's always a good idea to check that. You may have finished because you've passed the maximum number of iterations. And let's put out the answer as well. Initial velocity of V0 mid meters per second gives a final height of F mid. Now let's say a final height difference, actually, because otherwise that's not quite correct. In this case, because the final height we want is 0, then it would be the same, but in general that wouldn't be the case. Let's run it. Oh, I've put a mistake there. Oh yes, I forgot to put an equal sign. Let's run that again. Okay, so we have the initial line, the brackets, we have finished after 18 iterations, and we have an initial velocity of 49.05, gives a final height difference of 0.0006 meters. Okay, so that indicates that we've found an appropriate initial velocity. So that's a simple demonstration of how we code up the boundary value problem. So to start with, we code up the simple initial value problem solution for the ordinary differential equation. We then create a function which encodes the difference between the desired value and the actual value. Once we've got that, we can then use that in a simple bisection routine.